Full screen?
Yeah. It's full screen.
That's great. Great.
Okay, for some reason the live stream didn't work. It says you don't have permission.
Okay.
But hang on, let me, I thought I tried it.
That was always so
Can you
annoying.
give me 2 minutes? Hang on. Oh, wow.
So you are making the live stream?
Yeah, I'm trying that. Just hang on for a second, please.
Okay.
This sort of stuff can be tricky.
Yeah. Or we can start stuff together. Maybe I need to. Okay, why don't we begin? Maybe we'll try it next time. So let's begin. We'll just record it and upload it. So it's my great pleasure to introduce Liuquan Wang from Wuhan University. He is going to give a talk on the parity of coefficients of mock theta functions. Over to you, Liuquan.
So shall I start?
Yes, please, go ahead.
Okay. First of all, I'd like to thank the organizers of this seminar for providing this chance, and especially I want to thank Professor Batinaga for his kind invitation. Today, I'm going to share my research on the parity of coefficients of Modular functions. This was done in July in last year. And my talk will be divided into 4 parts. In the first part, I will give a brief review of the history on Modular functions. So we need this kind of Q-series notations, and I hope, I think everyone knows these notations. So we just have a quick look. So AQ sub 0 is just defined to be 1, and AQ sub n is the product of these n terms. Then if we restrict Q to have modulus less than 1 and letting n goes to infinity, we can define AQ sub infinity to be this infinite product. And sometimes we will deal with many such kinds of products. So we use this brief notation 0.3. We have the comma base Q, and then we have m parameters A1, A2 till AM. So this will mean the m product in the right hand side. And now we discuss the history on Modular functions. As we know, this was introduced by the mathematician Ramanujan in his last letter to Hardy, and the year is 1920. In that letter, Ramanujan gave a list of 70 functions which he called Modular functions. And now I got 2 pictures from the network. The left side is Hardy, and the right side is Ramanujan. So this is the handwritten letter, and of course we cannot see it clear. So I use this version from the book of Andrews and Berndt. This is Ramanujan's last notebook, part 5, the last the last volume. So the letter begins with, I'm extremely sorry for not writing you a single letter up to now. I discovered very interesting functions recently, which I call Moxian functions. And Ramanujan stated in this letter 70 functions. So in that time, they usually express the Q series in this sum in the Eulerian form like A and B in this page. And in that letter, he divided these Moxian functions into 3 classes, and one class of order 3, one class of order 5, and another class of order 7. So as we can see, the notation is like phi sub 3, psi sub 3, and chi sub 3. These are of the 3rd order. Because there are so many Moxian functions, besides the last letter, there are also some Moxian functions found in Ramanujan's last notebook. So to avoid confusion, I prefer to use a superscript n to indicate that a Moxian function is of order n. So based on the original notation, I will use f superscript n of q to denote the 3rd order Moxian function fq. And the other notations are similar. So in Ramanujan's original definition, this is given by equation 1.1, and this is a Q series of the Eulerian form. And similarly, there are several Moxian functions of order 5 and some functions of order 7. And as I said before, in his last notebook, Ramanujan actually recorded some identities for Moxian functions of order 6 and order 10. And here I just list the symbols for these functions, and I will not give the explicit definition unless we will meet them in the later part. And in 2007, Bruce Burnt and Song Hen Chan defined 2 new set of Moxian functions, phi minus and psi minus. So phi minus and psi minus actually comes from the original phi and psi of so original Moxian functions of order 6, which is phi and psi, and they just extracted part of the sums from the definition. And in the same year, Macintosh studied Moxian functions of order 2, and he used the notations A, B, and mu. And these 3 functions also appeared in Ramanujan's notebook. Earlier than that, in 2000, Gordon and Macintosh studied Moxian functions of order 8, and these are the functions they considered. So together, there are 44 Moxian functions, and in these 2 pages, and I will call these functions classical Moxian functions. It has been long time for people to understand the modularity of Moxian functions, because as we know, theta functions are important objects in the theory of modular forms because they have very good modular transform properties. But how about Moxian functions? Can we find modular explanation for these functions as well? If we just use the original definition, that is, if we just see from the Eulerian form, then we cannot see clear what it transforms like. So we need to find alternative representations for these functions. And it has been a long time for mathematicians to find such kind of simple representations. So with the contribution of many works, including papers of Watson, Andrews, and Hickson, Burnt, Chan, Choi, Gordon and Macintosh, Hickson, and many other mathematicians. Yeah, I'm sorry, here I cannot list all the names. So from their works, now we know that Moxian functions usually admit at least one of 2 kinds of representations. These 2 kinds are just, one of them is Aperionic series and another type is Hecke type series. So roughly speaking, Aperionic series are series of this form. It is also called Aperionic sum or Aper function. So the Hecke type series is a series of this form, where in the exponent of Q, we have 2 variables m and n, which take integer values, And we require that capital Q is a quadratic form and capital L is a linear form. And we require that the exponent is non-negative so that the series will converge. So these two kinds of series are very important, especially for that they served as bridges between modular functions and the theory of modular forms. In the 1930s, Watson found that for the third-order modular functions, they have some aperiodic series representations. For instance, for this function fq, he found that it can also be written as an infinite product 2 over qq infinity times another aperiodic series. And as we know, the product part is essentially a modular form. So to understand the modularity of fq, we just need to study the aperiodic series part. And similarly, for the fifth-order modular function, in the 1980s, George Andrews, by using the Benny lemma, he found that the fifth-order modular functions admit Hecke-type series representations. This is it was shown for as an example in 1.5 in this equation. We can see that f0 of q can be written as the 1 over qq infinity, the product times another Hecke-type series. So again, to understand the modularity, we just need to study the Hecke-type series, the modularity of the Hecke-type series. So as I said, these two kinds of series are the bridges. And using the aperiodic series or Hecke-type series expressions of these modular functions, such as the two given here, Sander-Zegers, around 2002, he fit modular functions into the theory of modular forms. And for more detailed introduction, I will recommend you to see the survey of Golden and McIntosh or the recent book of Andrews and Berndt, which I have just mentioned, and also the book of Breman, Foson, Ono, and Ronan, harmonic mass forms will also be a good reference. So as my talk is about the parity, the modular transform properties or the equivalent representations will not be the central topics. So what I am considering is about the arithmetic of coefficients of these functions. And this research was motivated by the leading research by Ramanujan on the partition function. So let's have a brief review on that. We need P of n to be the number of partitions of n, and in 1999, Ramanujan found that Pn satisfies some beautiful congruences, such as these three, and now they were recognized as Ramanujan congruences and are very famous in the theory of partitions. And because of Ramanujan's research, there has been a rich theory on arithmetic properties of various kinds of partitions, not only for the classical partition function, also for other kinds of partitions. And in contrast, the arithmetic properties of coefficients of modular functions were compared to the partition function were less understood. But in the last decade, there actually have been a number of works in this direction. So people have also studied the arithmetic properties for coefficients of modular functions. And since there are so many modular functions, I will introduce a unified notation here for our convenience. So for any formal power series G of Q with the nth coefficient being Cn, I will use the Cgn to be the coefficient of Qn in the series expansion of GQ. This notation will be very convenient for us because we just need to change G to discuss different when we discuss different functions. And in 2008, Gaswet and Peniston showed that the third-order modular function omega q, its coefficients satisfies infinitely many Ramanujan-type congruences. And in 2011, Waddell gave the first explicit examples of such congruencies. So he proved that C 40n plus 27 and C omega 40n plus 35 are both divisible by 5. So these are first explicit examples. And Bunier and Ono proved some nice identities and congruences modular 512 for this function for the coefficient of omega q again. In 2017, Andrews, Passeri, Senas, and E found more congruencies for this for the coefficients modular 4 and 8. And I found some similar congruencies modular 2 and 11. And I think the modular 11 congruency is quite interesting because Ramanujan's congruencies are modular 5, 7, and 11. So I think finding congruencies in modular 11 is quite interesting, at least for me. And later, Ernest Xia, he proved some congruencies for this function, again, modular 5. And Shen Chen and Chun Wang, they proved an infinite family of congruencies modular arbitrary powers of 3 for this function. Later, Renron Mo, he proved some congruencies modular 5 and 20 for the second order Moxia function B of Q. And Bernard Lin studied the 8th order Moxia function V0 of Q modular 7. And there has been more congruencies on coefficients of Moxia functions, and but I cannot list all of them here. So you may see the papers listed here and some reference in their papers. So although we can consider congruencies modular arbitrary integers, the difficulty depends on the modulus. Usually, we will expect that modular 2 will be the easiest one, but the truth is this is not the truth. So modular 2 and modular 3, even for these two smallest primes, there are some difficulty in doing this. So now let's consider the simplest case. That is, we consider the function modular 2, which is the parity. And to be for our convenience, we will use this definition. For any formal power series G of Q, we consider the parity of its coefficient. And if for given a positive integer m, if the number of coefficients of GQ module which is congruent to I modular m up to n, if such a number divided by n as n goes to infinity has a limit, and the limit, then we denote the limit as alpha sub I. So if this kind of limit exists for each I, then we will say that the function g and its coefficient sequence Cgn are of type alpha 0, alpha 1 till alpha m minus 1 modular m. So this is a definition was given by me. Actually, people will call this function, the sequence has some arithmetic density modular m. And in particular, when m equals 2, then there are only two density here, which is alpha 0, which means the density of the even values, and the alpha 1 means the density of the odd values. So when m equals 2, we will also say that g and its coefficient sequence are of parity type alpha 0, alpha 1. And it is easy to see from the definition that all this density adds up to 1. So as I have just said, modular 2 is actually not that easy, because it has long been conjectured that the partition function P of n is of type 1/2, 1/2 modular 2. That is, it will take odd values and even values half of the time. So if we write as this asymptotic formula in this equation 2.10, we will see that the number of odd values of P of n when n is less than 0, when n is less than or equal to capital N will be roughly 1/2 of n. And for this conjecture, Parkin and Shanks provided numeric evidence. They have two nuts of computation, which strongly supports that this conjecture is very likely to be true. And in 1959, Kohlberg showed that Pn actually assumes either even or odd values infinitely often. In 1983, Mirsky found the first quantitative result, which gave a first estimate on this on the odd values and even values. He showed that when n is less than capital N, the number of odd values is greater than log n over 2 log 2. And this is the first quantitative result. So far, the best known result for even values of P of n was given by Searle in the last century, in the end of last century. So he showed that by using the theory of modular forms, the number of even values of P of n grows faster than square root of n. So his proof is actually very short and easy to follow, but it is very mysterious why this record has not been broken. And the best known result for odd values of P of n was given by Benaich, Green, and Sundararajan in recent years. They showed that the number of odd values up to n is greater than square root n over log n. So these two records are based so far. But I'm not sure whether there are some new progress. So if you know some new progress on this topic, please tell me. Now let's see some other works on parity. Besides the partition function, people are also interested in other integer sequence, modular 2. For example, for the famous Rogers-Ramanujan identities given here, Gordon studied the parity of its coefficients, and he proved that the nth coefficient of GQ is odd for odd n if and only if 60n minus 1 is equal to p to the 4a plus 1 times m squared. Here p is a prime and m is an integer which is not divisible by p. And he proved a similar result for the coefficient of HQ. So this partially solves the parity problem for these two functions, because we should note that for even n, when CGN is odd, it is not clear, and for odd n, we do not know when CHN is odd. And based on this characterization, Chen proved gave some specific estimation for the number of odd values and the number of even values, and we can see that the main term are both 2 pi squared over 5 times n over log n, and the error term is also the same. So based on the previous works, this talk will mainly discuss the parity of coefficients of Moxier functions. So because there are so many Moxier functions, if we study them one by one, I think it is better to study them in the same time, because I think the methods are similar. So given a Moxier function g of q, our aim is to find its type modular 2. And if possible, we want to give characterizations for n such that CGN is odd. That is, we want to determine precisely for what kind of n CGN is odd and for what kind of n CGN is even. So this is our main result. We found that among the 44 classical Moxier functions, 21 of them are all of parity type 1, 0. That is, their coefficients are almost always even. And furthermore, for the functions in this list, except for the third order Modular function rho of Q, we can actually give characterizations for all the n such that Cg of n is odd. So what does this mean? This means that for 20 of them, we actually know very clear what the parity of their coefficients are. And for the exception one, for rho of Q, we have some partial characterizations. And actually, the functions given here can also be can be further divided into 3 groups according to their character. So the first group consists of these functions. So why do I list them in group 1? Because their parity shares a similar nature. For any function in this group, its coefficient is odd if and only if n equals to a quadratic polynomial of k. So that is Cg n is odd if and only if n equals to pk for some quadratic polynomial over of k. And hence the number of odd values can be precisely counted. So let me give one example. For the second order Modular function b of q, its nth coefficient is odd if and only if n equals to 2k squared plus 2k. And so we can give a precise counting on such kind of odd values. As you can imagine, this kind of results is not difficult to prove because actually the proof is very short. We just need the Heck-type series representation for this function. And this representation was given by Cui, Gu, and Hao by using Bailey lemmas again. So if we use the Heck-type series representation in the equations 3.1 and we modular 2 on both sides, then the product part, this part will be congruent to 1 modular 2, and this part, because it is symmetric over n, the summation is symmetric over n, so we will see that only the zero term when j equals to 0, when only this term remains when we consider it only modular 2. So after modular 2, we get after modular 2, we actually get After modular 2, we actually give a simplified version of this function. So b of q is congruent to 2. It's congruent to this theta series modular 2, and then we get the above theorem. So this the parity of functions in group 2 in group 1 is very easy. And then let's look at group 2. Group 2 consists of this kind of functions. So what is their character? What is their character? Why do we list them in group 2? The reason is that for any GQ from this group, the parity of CGN is similar to the coefficients of the Rogers-Ramanujan functions. And this group is, I think it is the most interesting group among these 3 groups, because to study functions in this group, we need both analytic and algebraic number theory. First, for analytic aspect, we need to generalize some estimates of Chen, and we give a snap generalization for his estimation. So this is our lemma. Let A and B be positive integers with A greater than B and A, B are co-prime to each other. Then we want to count how many integer n less than or equal to capital N, which satisfies that an plus b is equal to m squared times p to the 4a plus 1, and p is a prime which does not divide m. We want to solve this kind of equation and see how many solutions do we have. So we denote this number by gamma capital N. Then we find that gamma of n has the main term capital N over log n times some coefficient, and the error term is capital N over log square m. So this generalized the estimates of Chen because in his paper, he gave estimates for the two special cases when AB equals to 120, 59, and another case is 120, 11. And we also improved the error term from big O capital N log N over log square N to this error term, so that we can see the log N term was eliminated from the numerator. And for the algebraic number theory aspect, we need some lemmas from some classical book. Now let D be a square-free integer, and let K be the quadratic field Q at joint square root D, and we let O sub K be the ring of integers in K. Then we define capital D to be capital D as in this equation. We also need the following function chi of K. So given this quadratic field Q at joint square root D, we need chi sub K to be a function from Z to Z from integers and taking integer values. So the definition is as follows: when the variable x is not co-prime to capital D, then we need its value to be 0. And if they are co-prime, then chi k of x its value depending on the residue of D modular 4. So there are 3 cases here. And in the notation, A over B is a Jacobi symbol. So this definition was from the book of Shafarevich and Bowich. So why do we need this function? It is because we want to count the number of ideas in the ring of integers OK of norm n. And from that book, we know that the number of such ideas of norm n is equal to the sum of chi of m. And the sum is over all positive divisors over of n. And we will see, we can see that the function chi is multiplicative. So it is also clear that this function t of n is also multiplicative. That is, when m and n are co-prime to each other, then the value of t of mn is equal to tm times tn. Now we also need some other definitions. We say that two elements A and B in Z at joint square root D are equivalent if A divided by B is a unit in Z at joint square root D. And we need H of M to be the number of equivalence classes of elements in this ring with norm n. So these equivalence classes are defined because of we have an equivalence relation here. Well, we do not need to consider a general D, but instead we only need to consider 4 special cases. That is, we just need to take attention to the values of D when D equals to 2, 3, 6, or 15. And in the first 3 cases, this ring Z at joint square root D is a principal ideal domain. And for this case, it is very good. We can give explicit formulas for H of n. So we can actually count precisely how many such equivalences are for elements with norm n. And for when D equals to 15, this ring is not a unique factorization domain. So the case becomes more difficult. However, we are still able to find H of n for n in some special arithmetic progressions. So for I want to remark that for these 3 cases, the formula for H of n were also discussed earlier by Lovejoy, and we added several minor cases in his discussion. And for this case, it is new, as I cannot find any reference before. So let's look at this special case, D equals to 15. We have first, we can use the previous formula on T of n to give such kind of formulas. So this formula is follows from the previous lemma, because we know T of n is the sum of the sum of the chi function, and we can use the multiplicity of chi to derive this formula. So what we discover is the lemma 3.7, what I have written here. We found that in these two spatial arithmetic progression, 20n plus r and 40n plus r, here r, in the first case, r is 1 or 9, and in the second case, r is 26 or 34. In these four spatial cases, the value of h is the same as the value of t. So as we have seen, for t, we have this, the explicit formula 3.7. So in these four cases, we also have the same formula for h. And these are all what we need for studying the parity of modular functions. Now we just give one example. Why do we need this kind of formulas? Let's consider the fifth order modular function for psi 0. Its original definition is given by this Eulerian sum. And we get this kind of theorem. We find that the coefficient, the nth coefficient of psi 0 is odd if and only if 60m minus 1 equals to p to the 4a plus 1 times m squared for some prime p and integer m not divisible by p. So I think you are very familiar with these kind of numbers, p to the 4a plus 1 times n squared. This appears in Golden's work and also appears in our previous lemma on the estimation, right? Moreover, using the previous estimation, which we generalized from Chen's work, we can actually give an estimation on this on the number of odd values up to n. So we find that the number of odd values when n is less than or equal to capital N is equal to 2 pi square over 5 times n over log n plus this arrow term. So this estimation follows directly from our previous lemma. So what is the most important thing is this characterization. We find all the odd values of this function, this coefficient. So how do we prove this result? The proof, if we have all the ingredients as we stated before, then the proof will not be difficult. Once again, we need the Hecke-type series representation for this function, and this I think this was given by Andrews, maybe in this 1984 paper. Then we modular 2 on both sides. Again, this imbalance product will be congruent to 1 modular 2, so it goes away. And for this part, we because modular 2 -1 becomes 1, so we get this expression. And then we will analyze the exponent of Q. So we will analyze this exponent and by making it a complete square, we can show that C psi 0 n is actually congruent to half of the value of the h function at this number. So we have this kind of congruence. And then the problem reduced to study the parity of this function. But as we have already said, this function it is in the 4 spatial arithmetic progressions. So by the previous lemma, we know the value of this h function is the same as the t function. And for t function, we have the explicit formula. So by using the formula for t, we can see that this value is odd if and only if 60m minus 1 equals to this kind of number. So we prove the first part of the theorem. And the second part of the theorem just follows from the general estimation by setting A equals to 60 and B equals to 59. So this is a complete proof for this theorem. And all other functions in group 2 follow in a similar way. Now let's deal with the third group. In this group, we only have one function, that is rho of Q. And the definition for rho of Q is given by this unarial sum. So we can show that the coefficient of this function takes even values almost all the time, but we have not been able to find all the n such that 0 n is odd. But we still have some characterizations for some spatial for some subsequence. For example, we show that 4n, which means the 4n's coefficient of this function is odd if and only if n equals to 2k times 3k plus 1 for some integer k. And for the odd subsequence, 0 to n plus 1 is odd if and only if 6n plus 5 equals to this kind of number. Yeah, once again, we made this kind of number. And in a similar way, we can just apply the previous general estimation. We can get the number of such odd values has this kind of mean term and this kind of error term. So as we can see, for the subsequence 4n and the subsequence 2n plus 1, we actually know precisely when the coefficient is odd and even. So what remains? What's the remaining? The remaining case is for the subsequence 4n plus 2. So what happens for this case? For this case, we have this kind of result. We find that 4n plus 2 plus 0n is actually congruent to A3 of n over 2. Here, A3 of n is the number of 3 copartitions of n. Yeah, and I will not discuss this definition. So the parity of 0 at 4n plus 2 is determined by this 3 copartition function and its value at the nth term, at the nth place. And we find that at the subsequence 60n plus 2, its generating function is actually 2 times an infinite product. So at this subsequence 60n plus 2, its coefficients always takes even values. And by using the equation 3.14, we show that the coefficient of rho of Q actually takes even values almost all the time. So so this function is still of parity type 1, 0, but we still cannot find all the n such that its nth term is odd. Now we go to our last part of this talk. What happens for the other Modular functions? As I said, there are 44 classical Modular functions, and we have discussed 21 of them and divided them into 3 groups. So what's left are 23 classical Modular functions. For them, we cannot succeed in giving characterizations of their odd values. So what I can do is by using the computer, and we do a search for their coefficients, we make the following conjecture. So among the remaining 23 functions, 19 of them are of parity type 1/2, 1/2. That is, we conjecture that their coefficients takes even values half of the time. And for the remaining 4 functions, f0, f1, 2 times mu of Q and the lambda of Q, we conjecture that their parity type of 3/4 and 1/4. So here, why do we multiply by 2 for this function? Because in the original definition of mu of Q, we have half integer as coefficients, and we want, of course, we want integer coefficients. So we multiply it by 2. Although there are 23 functions left, some of them are related to each other. So actually, we do not need to consider all of them. Now let's give some examples for type 1/2 and 1/2. We can show that when G is with any of these 3 functions, f of Q, phi of Q, or the 6th order functions, phi of Q, the coefficient is actually congruent to P of n modular 2. So if we can solve the conjecture for P of n, then we can also solve this conjecture for these three functions. And this shows this problem will be very difficult. We can also show that when G becomes the second order Moxian function mu of Q or the eighth order Moxian function U0 of Q, the coefficient Cgn is actually congruent to P minus 3 of n. And here P minus 3 of n counts the three colored partitions of n. Similarly, we can show that the nth coefficient of S0 and S1 are also related to P3 of n. As for the 10th order Moxian function, capital X and chi, we can find this kind of reduction modular 2. That is, their derivative function are congruent to such kind of infinite products. Yeah, but this might not be helpful for studying their parity. Now let's give one example for the type 3/4 and 1/4. This is let's take the 6th order Moxian function mu of Q as the example. We can find that by using two dissection formulas, we can show that the generating function for this function for 2 times mu at 2n plus 1. For this subsequence, we can show that its derivative function is 2 times another infinite product. So this means that the 2n plus 1's coefficient is always even. And we can also show that the 2n's coefficient is actually congruent to P of n modular 2. So if we can show that the Pn is halfly even and halfly odd, then we can also solve this conjecture for this Moxian function. As I said before, there are some relations between the Moxian functions. Now let's see these two functions, psi of Q and lambda of Q. Though their definition is quite different, but we can show that C lambda at 2n plus 1 is congruent to C psi at n modular 2. So, and we can also show that the 2n's coefficient of lambda is odd if and only if n equals to a triangular number. And because of this theorem, we see that if we can show that the parity type of psi is 1/2, 1/2, then we can show that the parity type of lambda is 3/4, 1/4. So now let's see some data for which supports this conjecture. And we denote by delta Cnx to be the number of odd values when n is less than x divided by capital X. So this is the percentage for odd values among the first x values. And since there are some relations, as I mentioned before, between some of the Moxian functions, we actually only need to prove the conjecture for 15 Moxian functions instead of 23. So I list some data for these 15 functions here. As we can see, when we take x equal to 10,000, this ratio or this percentage is close to 0.5, which is 1/2. So this is a numeric evidence for the conjecture. Yeah, and as I think I still have some time, so let's discuss some further work. So in this talk, we have studied the parity of the coefficients of Moxian functions. That is Moxian functions modular 2. So a natural question is about Moxian functions modular 4. So in a recent paper by Rong Chen and Frank Gowan, they have actually studied 5 Moxian functions modular 2 and 4. So they studied the function a of q, v1 of q, phi minus q, sigma of q, and psi of q. In their paper, their notation is different from mine. They used the symbol capital N sub f of n to denote the coefficient of qn in the series expansion of fq. So in our notation, n sub f of n is actually cfn in this talk. So I will convert their result to this notation. they find that the coefficients of some Moxia functions are actually related to the Hurwitz class number. So we use Hn to be the nth Hurwitz class number. And they found that, for example, for the second order Moxia function A of Q, the nth coefficient is actually congruent to h of 8m minus 1 times minus 1 to the m plus 1 power modulo 4. So once we have this relation, to study the parity, to study the modular 4 properties of A of Q is actually reduced to studying the modular 4 properties of the Hurwitz class number. And for this class number, we already have enough knowledge for that. And they discovered, they proved this kind of characterizations for this Hurwitz class number. For n, for those n which is congruent to 3 modulo 4, they showed that 3h of n is odd if and only if n has this kind of form. So we meet this kind of number again. And they showed that 3hn is congruent to 2 modulo 4 if and only if n has this kind of form. This time we need two primes p1 to the 4a plus 1 power and times p2 to the 4b plus 1 power and times m squared. Here p1 and p2 are primes such that the Jacobi symbol of p1 or p2 equals to -1, and the m is coprime to p1 times p2, and a and b are non-negative integers. And with this theorem, together with the previous relation between A and H, they gave a characterization for A of Q modulo 2 and modulo 4. So this is their result on A of Q. They show that the first part is the same with the result in my paper, and so the methods improving. The methods used by them is different. They use the connection between AQ and the Hurwitz class number, and I use the hex type series representations. But they have more deeper results on A of Q modulo 4. They show that the nth coefficient of A of Q is congruent to 2 modulo 4 if and only if Hm minus 1 has this kind of form. And by using their congruence results, by using this theorem, they actually proved two conjectures in the literature. So one conjecture was proposed by Kim, Lim, Navjoy, and another conjecture is by Bryson, Ono, Pittman, and Rhodes. And they also pointed on an error in the original version of the conjecture. So there is in the end of their paper, they also asked whether one can generalize the results in my paper from modulo 2 to modulo 4. So it's especially I'm especially interested in the following question. Actually, after comparing the 5 functions in their list, as I said, they started 5 Moxia functions. So after we can see that all these 5 functions lie in group 2, and there are 8 functions remaining in group 2. That is psi 0, psi 1, capital F0, capital F1, and the other 4 functions. So my question is, do we have similar modular 4 properties for these functions in this for these 8 functions? Because their modular 2 properties are quite similar, so I believe that there are some similar modular 4 properties for these 8 functions. And again, since the F0 and F1 are essentially depending on psi 0 and psi 1, so we actually only need to study 6 of them. That is, we do not need to consider F0 or F1, so there are only 6 functions left. So if I wonder whether we can find some similar modular 4 characterizations for these 6 functions. And these are the main reference. So that's all of my talk. Thank you for your attention.
Thank you. Very nice talk. And very impressive work, I can say.
Thank you.
Any questions for the speaker or comments?
So Liuquan, I had one question.
Yes.
So you have done, first of all, very nice talk. So you have done it for mod 2. When you go to mod 3 or higher primes, there must be a lot of difficulties coming. That's what I envisage. I don't know.
Do you mean modular 3?
When you go mod 3?
Model 3? No, I have not. Yeah, I have not considered the mod 3 case.
Okay.
Yeah.
But mod 2 is the most famous, actually, right? Yeah, the one that you have.
Yeah. Mod 2 is very famous because of the partition function.
Right. Okay.
Yeah, actually, for the next project, I am more interested in the question I proposed here. I want to study the multiple properties of these functions. Because if you read the paper of Chen and Gavin, you will see it's quite interesting. And but their paper cannot deal with these 6 functions. So I wonder whether we can do it.
And they have a lot of mod 4 congruences as well in their paper, if I'm not mistaken. Chen and Gavin. Do they have
what?
Mod 4 congruences? I think they have.
Yeah, this is mod 4, right? Yeah, they have done mod 4 for 5 functions, for including this AQ and the other functions. Yeah, for these 5 functions, they have the similar mod 4 results.
Right.
Yeah, but for others, they don't.
Okay. Oh, good to know. Thanks for the nice talk.
Yeah, you're welcome.
Any other questions? Okay, then I want to thank the speaker again. Maybe you can open your mics and just clap.
Okay, thank you. Thank you.
Stop the recording.